fourth hour is hard when you sleep.
Who's covering somebody's going to be in the last hour, right? Like an hour before this?
Austin Taylor. Okay, so we're going to talk a little bit more about exponential and logistic modeling today. Yesterday we just talked about the functions. Well, yeah.
Was that a paper or was that
3.1 was a paper. Yeah, yesterday we had a paper. Yep. Yep, it should be over there. Okay, so you guys remember in the last problem yesterday how when we found the growth rate, it gave us like a number and then it told us the growth rate was a certain amount of percent. You guys remember that? So I kind of did that to introduce what we're doing today because the growth factors are 1 plus whatever percent that it's growing at. And then decay factors are going to be 1 minus whatever the decay rate is. So this relates to, we talked about this yesterday, so this relates to the function y equals ab to the x, which is our exponential function. And so these do have to do with the exponential function. But then we also have an exponential population model, which is something we'll use for population, and we could have actually used yesterday if it was something that we had known before. So what would P sub 0 stand for in the exponential equation? Yeah, so the initial amount, so it stands for what though? In our exponential equation, it stands for A. Remember, we put our initial value in for A, and so now we have P sub 0 as the initial population, and then we transformed the information we had to look like this. So where R is the rate that it's going up at, so we do 1 plus whatever the rate that's going up or down at, and then T is the time in years. So that relates to X. So we had B is the same as 1 plus the rate, and then our X is the same as T. So it's just a different way to write our population model for this one. And for this one, it's kind of self-explanatory, but if R is greater than 0, you agree that it's going to grow because you're going to have 1 plus something. But if it's less than 0, it's decay. Yep. Okay, so let's look at the first one. This X here is supposed to be an exponent. I'm not sure why it got brought down, but it's supposed to look like that. So if we have 550 times point, what? Oh, it doesn't. Oh, there's no symbol in between. Uh-oh. No, because it was supposed to be in there. But I caught it, though. I said times. Okay. So would this be exponential growth or decay? Decay. So why? Why would you say that? Because why? It's less than 0? Yes, because b is less than 1. Okay, so what would be the constant percentage rate? If we think of it as we have up here, they have it in a percent. But how could we find it from the information that we're given? Well, but this is a decay, right? So how could we find it? If you look at where it says exponential decay factor, so how could we find it? Say it louder, Aaron. So yeah, do 1 minus that number that we have. And what is that going to give you? Nobody got anything? Or nobody did it? What? Okay, 32,000. Good. So we should have that. So how would that change to a percent? Supposed to be 0. So how can we change that to a percent? If it's that as a decimal, what percentage is it? 0.32. So we'd say it's decaying at a rate of 32, right? 0.32%. And so it's decaying at a really small rate, actually. But this one, it's still considered decaying because it's going just a little bit at a time. Okay, so I'm sure tomorrow we're talking about the population, so we're going to use more of the population model, but today we're going to talk about more. Have you guys talked about like exponential growth and decay in like science, I'm guessing, with like species or all different stuff, freshman year? Okay. Okay, so if we think of our exponential equation for number 1, who can tell me how we could put that in to our exponential equation, the information that we have? Because we have a culture of 100 bacteria, and it's put in a petri dish and doubles every hour. So we want to find out how long it takes to reach 400,000. So let's just look at the first part first. And what? What do you guys think? Good. 100 times 2 to the x. Does everybody see where we got our 2 from? Because it's doubling every time. So it's like if we said if you think of this as like, so it's 100% more every time. So you're going to have 1 plus 1 gives us 2. If you think of that as like 100%. Okay, so if this is how we write the actual equation, then how could we find out when it's going to reach 400,000? Graph it. And put it, what? Equal to 400,000. Good phrase. So we want to find out when our function is equal to 400,000. Okay, so something to think about, your window has to be really big, right? Because you have to have it at least 400,000. So my Y is 500,000 and mine looks something like this. Did ever you get something like that, whether it was closer or further out? Is anybody not sure how we got that? Okay. So what did you guys find? Where do they intersect? I don't.
It's gonna be a little under 12.
It's a little under 12.
11.97.
Yeah, 11.97. Make sure you type your equation in. Yeah, okay. So it should be, x is about 11.97. So if we want to change that to hours and minutes, it's 11 hours, and how would you find, oops, it's 97. How would you find out how many minutes that would be? About. What would you do with the 0.97? Figure out how many minutes. Multiply by 60. So it's about 11 hours and how many minutes then? What does it say? 11 hours? And then we're trying to find out how many minutes 0.97 is. Does anybody get it? 56?
Why would you write 11? Wait, no, the 0.97.
Nope, so we're doing 11 hours, and I want to find out the amount of minutes. Like, it's going to be 50, so we're going to say 11 hours and 58 minutes. We wanted to find a more exact, yes, it is very close to 12. We're just trying to find both the hours and minutes. Why would it not be what? 59. Because it was closer to 58. If it was higher, I would have rounded up. But I just wanted to have hours and minutes.
How did you find that one? How you found it?
How I found the what? The 11?
No, the minutes.
How I found the minutes. Oh, we did point. So we did 97 hundredths times 60. So could you guys, if you knew that 0.2, what was left over, couldn't you have found the second 2 realistically?
Yeah.
If you just multiply that by 60? Okay. So I want to show you guys, how many of you guys remember logs from? No? A couple of you? Yeah, so how many do you think that you could solve this using logs if I gave you the chance? I multiplied 9,700 by 60 to get this. Does anybody think that they could successfully solve this with using logs?
No.
Don't be shy. If you have a pass. Okay, so you guys aren't expected to do this right now, but eventually we're going to be using logs, so I want to show you guys how we can do this. What? Eventually in this class. Okay, so if we want to solve for x, what would we do first?